and others. Hello, Erica. We are doing the second half of 3.6, which is inverse functions. All right. Down on horizontal line test. Are you ready? Horizontal line test. Okay. I'm going to be very clear about this because people get this confused. Okay. Are you ready for this? Horizontal line test. Let's say that my original function is this guy. Okay. The original function is this guy. Write this down on horizontal line test. Write this. Keep this clear. The horizontal line test, okay? If I would, that's my original function. If I would do the vertical line test, does he pass?
Yes.
Yeah.
That's a pass, which means he is a function. The original one is a function. The original guy, this guy himself is a function. Okay?
Gotcha.
Now, if I want to know whether or not his inverse is a function, is his inverse a function or not a function? Is his inverse a function?
No.
What I do is the horizontal line test. Okay, the horizontal line test. Does he pass the horizontal line test? No, he's a fail. So that means his inverse is not a function. Okay? What is the inverse of that parabola look like? Like on a graph?
On a side.
On his side, okay? This is the inverse. Is this thing a function? No, that thing is not a function, right? Because if I do the vertical line test to this guy, it tells me he's not a function, right? But I don't have to actually draw the inverse out to know whether his inverse is a function or not. I do the horizontal line test. This is what he actually looks like. Vertical line test says he doesn't pass, but I can tell that by just doing the horizontal line test to that guy. Does that make sense? Okay? So you do the vertical line test to determine whether what you're looking at is a function or not. You do the horizontal line test to see if what you're looking at, his inverse, is a function or not. Happy with that? Okay? All right, good. Let's go to the back side. Here we go. Use the horizontal line test. Okay. A. Graph each function below and determine whether the function is 1-to-1. If so, graph its inverse. Okay. So it's saying, is his inverse a function? 7x to the 5th power plus all that other good stuff. We're trying to figure out whether his inverse is a function. Okay? Somebody want to slap that on a calculator for me real quick? I'm going to guess he's a no. If he has some sort of bubble in him, he's definitely a no. But let's see. A. Somebody slap that on a calculator and tell me. While we're doing that, somebody graph B and somebody graph C. A couple people. If you have your calculator, take it out. A couple of people graph A, a couple people graph B, a couple people graph C. Okay?
I'll graph C.
And then tell me when you've got it. Put your window negative 10 to 10. Okay, this is A? Okay. Nice. So A just looks like this. This is A. A. Okay. B. I'll put B over here. And C. B, C. Tell me when you got one. Somebody get B, somebody get C. This is B. Okay, B looks like this.
Here's C.
This is B. Here's C.
Yeah.
Perfect. C. Okay. C looks like this when you graph him. Okay. A, B, C.
Yes, no, yes.
Okay. A, B, and C, are they all functions themselves?
Yes.
Yeah.
They all would pass the vertical line test, right? Okay. A, will he pass the horizontal line test?
Yeah.
Yes, which means his inverse is a function. Inverse, yes, function.
Regular?
Okay, the inverse is yes, a function on A. B is the inverse of function. No, like through here, he's going to cross multiple times. So I'm going to say inverse, not function. Okay, the inverse will not be a function. What about C? Inverse, yes, function. He will pass the horizontal line test. Okay, each one of these functions themselves is a function, but their inverse is not a function. Now, that doesn't mean they don't have an inverse relation. Like, you can still find the inverse of them, but their inverse is actually not a function. It doesn't pass the vertical line test. Okay? Good? Are we clear on that? Okay, don't get that confused. All right, let's go here. Example 5, restricting the domain. All right, if we're talking about x squared, what does x squared look like? Let's do that real quick. What does y equals x squared look like? What's this original function look like? This is my original. It looks like a parabola right here like this, okay? Does his inverse is his inverse a function?
No.
No, okay, but what we're going to do is it says find an interval on which the function is 1-to-1 and find the inverse on the interval. What is the inverse of x squared?
Y squared.
Kind of, but what's the
square root of x.
It's the square root of x, and technically it's plus minus the square root of x, right? Okay, so basically y squared, right? Okay, so this is what he would look like. Now, he is not an inverse, but is there a way that I can restrict him so that he is then a function,
Plus.
right? What?
Get rid of the minus.
Get rid of the minus, right? I like get rid of this part, right? Okay? What that's going to do is that's going to get rid of this half of the original. So it's basically saying for the original guy, in the original guy, if I restrict his domain, restrict the domain, D-O-M-A-I-N, of the original guy, if I restrict the domain of the original guy so that he's only this chunk of the parabola, do you see that, this little piece right here? What would his domain look like if we only want this right half of the parabola? X has to be greater than 0. If x is greater than or equal to 0, his inverse will only be the positive square root, and he won't be the negative side as well, right? We get rid of that other half of the parabola, he'll only be the positive square root. Okay? Now, you could have said also x is less than or equal to 0, and ignoring the right half of the parabola. Is that still going to be a function as well? It would be just the bottom half. It would just be negative square root of x, but that's still going to be a function because it'll pass the vertical line test, okay? So whichever way you decide to do it, x is greater than or equal to 0 or less than or equal to 0, as long as you cut off half of the parabola, it's going to be a function now. Yeah? Ish? Okay? Okay, all right. Next really important thing, last really important thing. Ready? If two functions are inverses of each other, listen to this really carefully. These two functions, if they are inverses of each other, here's what happens. Are you ready? This, we have a function f, is what they call it, and we have a function g, which is this guy, okay? If those functions are inverses of each other, here's what will happen. We can stick one inside of the other, like f composed of g. And then we can stick g composed of f. We can stick them vice versa, and something extra special will happen. It will be equal to x. Equal to x, okay? Everything else will cancel when we simplify except for x, right? Okay, let's see if that happens. So if I do f composed of g, that means I'm sticking g into f. I'm sticking g into f. We talked about this on Friday, didn't we?
Wait.
It'll all reduce to be x, okay? Stick g into f. So 5 over 2x minus 4, right? And this will be, oh boy, 4x plus 5 over 2x. Okay. All right. Oh, what a mess.
Can you just multiply the
Can
twos through everything?
we cancel the 2's? We can cancel the 2's. Okay, so that does that. Oh, heavens. Okay, so now we've got this bottom part. We've got 4x plus 5 over x minus 4. Okay, I want to have a common denominator of x. So this would be like minus 4x over x. You see that? If I make it a common denominator, it would be minus 4x over x. You see that? Okay, then what happens? If I simplify this stuff on the top. 4x's go away, right? So what's left on the bottom? 5 over x. And up here is 5. So I have 5 over x. Ooh, what a mess. And then what? How do I divide by a fraction? You multiply by the reciprocal. So I multiply by x over 5, yeah? And then what happens? The 5's cancel, and so all I'm left with is X, like I'm supposed to, right? Okay? All right, now let's check the other direction. So here we're plugging F into G. Let's hope this one goes a little bit better. Oh my gosh, this is crazy. Okay, let's plug F into G. All right, so G was 4x plus 5 over 2x. What a dang mess. 5 over 2x minus 4. And 5 over 2x minus 4. Holy crap, this is disgusting.
Hey, whoa.
What?
We say that the top is twice as big as the bottom, so it's 2 over 1. Or no?
No, because it has this plus 5 on here.
It'd be easier to go the other way because that only has one x.
What are you talking about?
Can you
What?
reduce the two sides? and
Plug
then-
in 4x plus 5, 2x into 5, 2x minus 4 because that only has one x and the other one has 2.
That's what we did over here.
Hey, time out. Can we
That's
have-
exactly
you
what we
know
did
it.
on this side.
You don't have to do it again, right?
Yes, you do.
You do?
Because sometimes one will end up being X and sometimes the other one won't. Very rarely does that happen. Usually if one side is X, the other side is also X. But
Okay, hey.
every once in a while you'll have it come through where one side comes out nicely and the other one doesn't. What?
Okay, so set it equal to 0. Multiply the bottom over.
You can't set it equal to 0.
Why not? It says
We're just
2x.
simplifying.
Can
You
you
can't set it equal to 0.
can you make it 0 on the bottom and have it 2 on top?
What if you plug in a number for x and that would just make it easier?
Plug in 1.
You can plug in the same number. If you plug in 1 for x and you get out 1, then that'll be correct.
Oh.
Why don't you just do that? That would make it so much easier.
Hey,
the things should
that's
go away.
a good idea.
That's called
Let's
thinking
plug in
with your
something
brain.
weird though. Let's plug in like 7.
No,
Let's put in 1.
No, because
then the
a lot
x
of
would
times,
go
a lot of
away.
times it'll simplify to be 1 though when it's not actually like 1. You know, 1. You know.
It's fine.
So
but
3.
it's not that much more.
Let's do 5.
5 is acceptable.
5 is acceptable. Okay, so he's saying that this, if it ends up being equal to x, he's saying let's not simplify it. Let's not simplify it. Let's instead plug a number in for x and plug the same number in down here. And if it truly is equal to x, we should get equals that number out, correct? Does that make sense? Like if we plug a number in, we should get the same number out if it should be equal to x, right? If everything reduces to x. Okay, so let's plug in 5. I want to plug a weird number in, not like 1 or 2, because a lot of times like those naturally just come out to be 1 or 2, right? So 5 or like something like 7 or something weird, right? Okay, so if we plug 5 in, 5, got it, 5. All right, what is 5 over 2 times 5 minus 4? 5/6. 5 over 6. Okay, so this becomes 5 over 6. Great. Holy crap. And this becomes 5 over 6 as well. Yuck. Yuck. Okay. 4 over 1 times 5 over 6. That is 20 over 6. We have 20 over 6 plus 5 on the top. Okay, on the bottom, that will be what?
10 over 6.
10 over 6. Okay. If I add 5, let's see if this comes out. If I add 5, this is like 5 over 1, right? That would be 30 over 6.
50.
So that is 50 over 6 over 10 over 6. Hey! Then what?
Hey, me.
Hey.
You. It's 5.
Times 6 over 10. The 6's cancel. What's 50 over 10? Boom. Check. So we just like didn't do that the way that they wanted us to, but we did it by like plugging numbers in. That's totally legit. That's fine. So what would have happened is that would have come out to be x, right? Okay, now hold on. Why does it come out to be x and not like 0 where everything cancels out, or like 1?
Because y is equal to x.
Because the graph, yes, exactly. The graph where we talked about the front side, if they are inverses of each other, they are reflections across the line. Y equals x. That's why when you put them inside of each other, it cancels out, right? Yeah? Okay, so that was when they say, on your homework assignment, when they say verify using composition. Composition, that's what you're going to do over here. Composition means stick them inside of one another and see if it comes out to be x. That's composition. Composition is like F composed of G or G composed of F. That's what they're asking for. They want to see if it comes out to be x each time, yeah? Woo, that's lots of stuff, all right? Good? Okay, you guys should have the homework assignment for this. Do you have it?
Yeah.
Do you need it? You got it.
Okay.
Okay,
I need you now.
Do you need
there you
3-5?
go. I'm gonna walk around while you guys use time to work. I'm gonna walk around and help people who are gone if they need it. And yeah, there you go.
Can I
Okay?
see my calculator?
Yes.
I'm gonna
Okay.
wait.
I need help.
I
All right.
know-
Hold on. Goodbye to Erica.
1, 2, 3, 4.